Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Double Integrals and Such. And as always, I encourage you to be an active learner as you watch this video. In this section, we learn how to evaluate a double integral. We solve applied problems involving double integrals, and we find the average value of a two-variable function over a given region. And the technique that we use to evaluate double integrals is called iterated integration. And let's do an example to make this be very clear what we're talking about, and then we'll define it more formally. So the following is an example of a double iterated integral, or a double integral. And so we have the integral from 3 to 6. That's a definite integral. And by the way, these match up. So this is on the outside, so this range is for y. So y is going from 3 to 6, and if you look down here, here is the x-axis, here's the y-axis, this is the z-axis. So we're going from 3 to 6, but that's the y. So that is the dy, and they match up because they're on the outside. But inside, we go from -1 to 2, and that's what x goes from. And the function, which is going to represent the height, is going to be 10x y squared. Now, so this integral, this one, matches with the x. And that's exactly how we will evaluate this integral. We'll do the innermost one first, and then we'll do the outer one. So the first task is to integrate this one. But here we're integrating dx. That means that y is a constant. So we're treating y as a constant. So the integral is 10x dx. And the y squared is a constant. You could think about that pulling it through the integral. So you see we have 10 and y squared are constants. We have them outside. They're integrating x dx. And that's going to be add 1 to the exponent, divide by the new exponent. That's going to be x squared over 2, evaluated at the endpoints, and subtracted. So you see this 2 cancels into that, making that 5y squared. And then I can just evaluate x squared 2 minus x squared evaluated at -1. I do that calculation, and here I get that this is going to be 15y squared. So when I integrate this inner integral here, I get 15y squared. But now I have to integrate from 3 to 6. So I go out here 3 to 6, but now it's 15y squared. Add 1 to the exponent, divide by the new exponent, I get this. 3 goes into 15 5 times. Then I evaluate it at the top and the bottom, and I get 945. So you see that is the integral. This iterated integral is 945. Now, if dx and dy, as well as the limits of integration, are interchanged, we have this. Now notice that we moved this one to the outside, we moved this to the inside, and first we have dy and dx. Let's see how this one would work out. So here, first we integrate with respect to y. That means x is a constant, so I pull out the 10x. I add 1 to the exponent, divide by the new exponent, and I use the fundamental theorem of calculus to evaluate that. And I get this 630y, 630x is what I get for evaluating this, the innermost integral. But then I have to integrate this answer with respect to x with the outside one. This goes -1 to 2. I add 1 to the exponent, divide by the new exponent. 2 goes into 630 315 times. And I evaluate this using the fundamental theorem of calculus, and I get the same answer. So this motivates the definition then. If f of xy is defined over a rectangular region R. Now it's different if it's not a rectangular region R, but a rectangular region R divided by x runs from a to b and y runs from c to d, then this double integral is given by this iterated integral or this iterated integral. And notice that what we've done here is we've switched the x's and y's, dx and dy's. Under very general circumstances, those will give you the same answer, just like they did in the example we just talked about. Now, in a more technical definition of this, we would actually use Riemann sums. And what we would do is we would slice up this rectangle or the area down here into little squares. And then what I would do is I'd have a function up here, and I would be evaluating that, and you see that that's going to represent a three-dimensional figure, and that's going to be volume rather than area. But for now, and in this textbook, the above definition is sufficient. Now, sometimes double integrals are defined over non-rectangular regions. In fact, this happens more often than not, in which the bounds of the variable of integration may contain variables. So you see here we're integrating over this region R. Now, x does go from 0 to 1. But for every fixed value of x, what happens is this region, you go from the lower curve, which is y equal x squared, to the upper curve, which is y equal x. So in this example 1, we're evaluating the definite integral from 0 to 1, the integral from x squared to x, y squared dy. And you see the dy is the first one you do, and the dy corresponds to this integral sign, and the dx corresponds to this integral sign. So this is what we're going to be evaluating. So we, again, evaluate the inner integral first. So we evaluate this one first. So we go from x squared to x of x, y squared dy. Now we're treating x as a constant, so we can pull out the x, and these variables are also, these limits are also constants. The top one is x, the bottom one is x squared. But now we find the antiderivative of y squared, which is y cubed over 3. So I start plugging in, this x is still on the outside, I plug in x minus plugging in x squared. That's what we do here, and this is what we do to simplify. So now you see we have done the dy integral, and we have this. Now, so we've calculated this, so now we're going to integrate from 0 to 1 of that answer, dx. And so we do that, and we're going to be able to pull out the 1/3. We have this. We add 1 to the exponent, divide by the new exponent both times, and use the fundamental theorem of calculus to evaluate this. Make sure you're following these calculations, and we get 1 over 40. So the answer to the problem is 1 over 40. Now, as I said before, the geometric interpretation, if we had this, where x was going from a to b, and then y was going from this lower function g of x to this bigger function h of x, we could think about cutting out little rectangles here, or squares, I guess. And what we would do is we would be getting a volume, because the z, the function value, would be the height. So this is z equals f of x. And you see, so volume is going to be the integral from, and this is y first, so we go from g of x to h of x, and then we integrate this from a to b. That's going to give me the volume. So the geometric interpretation of this integral is that we have volume. Now in example 1, we did do an integral, and you can look back on the one we did, but that does represent a, and so this was the region in the xy plane where we got the dx and dy, but we have the height, and this was the function we integrated, which is z equals f of xy is equal to xy squared, whose graph looked like that. So that is the volume that we actually calculated. Life is a word problem, so let's talk about a word problem. Now this is going to build upon the problem that we already did. So the density of a privately owned vehicle, so this is the density of the privately owned vehicles in this town, is given by P of xy is equal to 1 over 8 xy. Now remember that that was or actually I guess we'll do it this time. That's one that we're going to calculate, and you want to remember the results because we use it later. So x is the number of miles from the southwest corner, that's down here, of town in the east-west direction, and y is the number of miles from that corner in the north-south direction, and the town's shape is like this. So you see, if we fix x, y is going to be integrated from, so fixing x, we draw a slice here, and y then is going to go for any value of x that's fixed. We're going to go from 2x up to 6. So, and we want to, so let's see, so where were we? And P is the number of privately owned vehicles per square mile in thousands. If the city limits are as shown, what is the total number of privately owned vehicles in the town? Well, okay, so this is the integral that we talked about that represents that. So we're going to evaluate this. First we integrate with respect to y, and this is going to be 2x is this bottom curve, and the top curve is 6. So this goes from 2x to 6. This is 1 over 8 xy dy. So we move out the 1 over 8x, that's a constant. We add 1 to the exponent, divide by the new exponent, evaluate at the top limit and the bottom limit, and substitute those in. We get this. Simplifying, we get this, and then this. Make sure you follow all of these calculus steps and the algebra steps. Then, we've calculated the inner one, so now we're going to integrate from a to b that answer. So this was the answer. We integrate from 0 to 3 because the x value goes from 0 to 3. So we integrate this. 9 over 4 can factor it out. We add 1 to the exponent, divide by the new exponent. And this is the 1 over 4 factors out. And we add 1 to the exponent, divide by the new exponent. We get this, 3 and 0. We evaluate this using the fundamental theorem of calculus, and we get 81 over 16. So this iterated integral is 81 over 16. And that means that there are 5063 privately owned vehicles, if you round it off. Now, another concept, we're going to talk about the average value of a function. Now, you might recall that when we had a function of one variable, where y was equal to f of x, the y average over an interval ab was 1 over the length of the interval b minus a times f of x dx. So that was the average value of a function in a previous chapter. Again, good review for the final exam. In 2 dimensions, we say, let z equal f of xy be a continuous function over a region of integration R in the xy plane. Now, so the region of integration is R, and that's a region in the xy plane. So the average value of z, that's our function z equal f of x, over R is given by z average is equal to 1 over, this is the area of R, and this is the double integral over region R of f of x dy dx, where a of R is the area of the region of integration, and R is used to determine the limits of integration. Okay, so now we're going to revisit our example 2, but you might remember that this was what we've had for the region, and we also calculated the function before. So we're going to find the average value, or the average number rather, of privately owned vehicles per square mile. So it's this triangle, and the area of a triangle is 1/2 the base times the height. So this is 6 and the height is 3, but it's 1/2 the base times height, so the area of that region is 9. So this is going to be 1 over 9 times this iterated integral. But we calculated that before and we got this. So if we multiply those together, we get approximately this. So we have approximately 563 privately owned vehicles per square mile. To summarize this section then, the double integral is defined this way and over a rectangular region, and we can switch the order of integration and we will get the same answer. That's when it's a rectangular region defined this way. If the region is not rectangular, the double integral may have variables in the bounds, and we talked about calculating those. We also learned that the average value of a continuous two-variable function z equal f of xy over a region R is given by z average is equal to 1 over the area of R, and this is the double integral over the region R, f of xy dy dx. And again, a of R is the area of the region of integration, and R is used to determine the limits of integration. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.